Now see what what we before that we assume that in the modeling of the problem. Now first of all we'll start with the initial flow, which represents the stationary state. Means actually we'll start with the stationary velocities. Okay, so here first of all we'll start with the stationary velocities. So we are assuming that this is also assumption only. We are assuming that u bar is equal to u r, u theta, u z, and the u r we are taking at the basic velocity. This is the stationary solution. We are taking it as 0, and u theta equal to vr, and the u z is equal to wr. Actually, we can say along the y direction, the velocity is vr. Along the z direction means like this. It will go up. Okay, and along the z direction, the velocity is wr. These are depends upon, these are the functions of r. Okay, and we are assuming that ur is equal to 0. This is the stationary uh, basic stationary solution. We are saying that. Okay, now similarly, now p is equal to rho into integral v square by r dr. So finally these are all functions of r. Okay, now and we are assuming that these all values are depends functions of r, and we are saying that the perturbations, means the disturbances, are very small, which are independent of theta. Okay, now and let us assume that there is a small disturbance in these velocities. There is small disturbance in the flow. Okay, now in the basic velocity ur, there is a small disturbance. So along with the x direction, we are saying disturbance is ur bar. Along the y direction, we are saying the disturbance in u theta, that is u theta bar. Along the z direction, there is disturbance in the velocity, that is u z bar, and p also, the pressure also. So that is the disturbance is del p. These are the small increments in all the variables. Okay, so u bar, ur bar, u theta bar, u z bar, and del p are the disturbances, means the small disturbances, small increments, we can say, which are functions of r and z only, not theta. Okay, now when we apply when we take these stationary solutions in the previous equations, means like in equation 6, if you take it, they will get dou u r by dou t, means u r replaced by 0 plus ur bar, and u theta is replaced by vr u theta bar. Similarly, u z is not there here. P replaced by p plus del p. Okay, after simplifying this, we'll get this expression. When you observe this here, we got one term, that is a whole square, vr plus u theta bar whole square by r. Okay, when you expand this, we'll get v square by r. Okay, v square, what is v square by r actually? Now we are saying that this p is the rho, p equal to rho into integral v square by r dr. Okay, when we are writing this side, we'll get p by rho, and if you are taking the derivative on both sides, we'll get dou p by dou rho equal v square by r. So that is what we are getting in this here. So we'll get v square by r. This gives the dou p by dou r. Okay, so here these two terms will be cancelled on both sides, and after simplifying the expression, we'll get equation 10 like this. Okay, similarly, from the above equations, Euler equations, we'll get these three equations we'll get, and after implying the stationary solution in the equation of continuity, we'll get the equation 30. Okay, now what we do now, we'll follow the linear stability theory. Linear stability theory means what? We'll neglect all the products and the higher powers of the increments, and we'll retain only the linear terms of the increments in these equations. So we'll follow the linear stability theory. So neglecting all the perturbations, neglecting all nonlinear terms of the perturbations. Perturbation means increment or disturbance. Okay, so if you neglect all the nonlinear terms, if you neglect all the nonlinear terms, so we'll get the new equations like this. Equation 14, 15, and 17 will get, and these are the equations which we got from the Euler equation and continuity equation after taking the linear stability theory. Okay, now how this disturbance will be? How this disturbance will be? Disturbance will be less or more or high. Okay, if it is the disturbance is high, what we can do? So that we are using the normal mode approach to to analyze the disturbance. Okay, normal mode approach means we'll take the disturbances are very high. Let us take, we are assuming that if your disturbances are very high, then that will be implicable for the lower disturbance variables also. Okay, so if you are taking the disturbance is very high, that approach is called normal mode approach. Okay, in this we are we will say those disturbances are only the functions of z and t in the normal mode approach. Okay, now in normal approach we will express the increments or disturbances of the velocities in terms of exponential. In terms of exponential function, exponential means it is high, the disturbances are very high, we are saying. Okay, so if you are taking these exponential disturbances are high, we can implement this disturbances for the small also. Okay, so in the so we are taking ur bar equal to ur into e power I pt plus kz, ut bar equal to vr, the same thing, and the uz in terms of exponential term. Okay, p also same, p equal p of r e power I pt plus kz, where this p is the constant and k is the wave number, we can say, and the disturbance in z direction only. Okay, and where this u r, v r and w are the, and p r, p of r are amplitudes of the perturbations, u r or u to the bar, z bar and the del p respectively. Okay, now so if you use this new normal approach mode in our previous equations of 14, 15, 16 and 17, now we'll get the new equation like this: I into P kW minus 2 rho V equal to minus del omega bar. So where where rho equal to omega equal to V by R and W bar equal to P by rho. Okay, from the above equations we'll get these four equations. Okay, and this is a very important one: I P plus kW V equal to minus U into D star V, where D star is the D plus 1 by R. Okay, so finally what we do, we'll obtain the relation between these four equations. Will come to the, will model our problem for the given fluid. Okay, so first of all we'll compare these two, 20 and 21. This is actually W bar. Okay, so we'll compare these two, then we'll get equation, this equation, and we have W bar and we have dW bar in equation 18. So what we do, here we can differentiate this equation with respect to d, and we can substitute that equation 18 here in the next in the following relation, so that we'll obtain our problem like this: W plus P by K into D star minus K square into U minus R into D of dW by R, U equal to 2ik rho into V. Okay, so finally we'll take this P by K as minus C. So we can obtain the equation like W minus C D star minus K square into U minus R into D of dW by R into U equal to 2ik rho V. This is the this problem represents the motion of the fluid which is there in the two concentric cylinders. This is the non-homogeneous differential equation. But if we take this rho is equal to 0, we'll get this part equal to 0, that is W minus C D star minus K square U minus R into D of dW by R into U equal to 0. This is called a homogeneous part, and the name of this is called a circular Rayleigh problem, where the boundary conditions U of R equal to 0 means U of R1 and U of R2 both are equal to 0. So this represents the fluid flow between the two concentric cylinders, but which is homogeneous. Okay, so we worked on this and we got very good results on this problem. Yeah, this is derived by Sir Chandrashekhar in 1961. And here, what are the terms involved here? Let me explain about all these terms. D star, here D star is nothing but D plus 1 by R, where D is D by dr. And this C is the complex eigenvalue, which involves CR plus ICI. These CR and the CI are the real and imaginary parts of the complex eigenvalue C. And that's actually we are locating the point C this with this C only we are going to find out where is the instability region. Okay, and W is the velocity function, and U is we can say in mathematical word we can say U is the eigenfunction, and K is the wave number. Okay, now this is the literature review. Many researchers they did so much research on this problem. Now, first one, Chandrasekhar in 1961. Now, he proved that the necessary criterion for the instability, that this term is called verticity function. Okay, this term is if this term changes at least sign once, that is the instability. That is the necessary condition for the instability to get it. Okay, and later Pavitra Subbaya in 2019 she got one more criterion for the necessary condition of instability region, that she got one more extra term, that W minus WS, means the verticity function multiplied W minus WS is less than 0. This is the condition for the necessary condition for the instability region. Okay, similarly there are more results, and this result is main thing. Batchel and Gill semicircle in 1962, he proved that the instability region is lies within the upper half of the semicircle. Okay, actually he located the complex phase velocity, means complex eigenvalue C, where it lies in the upper of the semicircle. Actually we are going to locate where the solution of the circular relay problem is not exist, means we are going to find out where these eigenvalues are located for which the solution is not exist, means you can say it is unstable region we are going to find. Batchelor and Gill, he found that the instability region is lies within the upper half of the semicircle. That I will explain through graph itself. Okay, so these are the some of the results which are review, literature review of me, and this is the heterogeneous problem. Okay, some literature review. Now here my results, that is on the improved instability region for the circular relay problem. Okay, this is the circular relay problem which are already given, and the Batchel and Gill semicircle. See, this is what Batchel and Gill proved, that is CR minus this value whole square plus CA square less than or equal to this value whole square, means if you are considering this CR is X, okay, if it is, let us take this CR is X, okay, and this CA is Y, then what it represents? It is represents like a semicircle. Okay, so means we are locating the values of CR CI where it exists, so we are locating these values under the above the semicircle. And Batchel will saying that the instability region is lies within this semicircle. Now we are comparing, we got results and we are comparing our results with the Batchel and Gill every time. Okay, now the first result which you got it, that is if modulus of W minimum is positive and C is greater than 0. Actually this is CI means for the instability this should be there. Okay, CI greater than 0, then only the instability region will get it. Okay, if W minimum is greater than 0, then this results happen, means what, CI square less than or equal to lambda into CR minus this value, means again is the same thing. If you treat this is X and this is Y, this represents the parabolic region. Okay, means CR and CI values lies within the upper half of the parabola. Okay, and where is the validation here? How to compare? Now what we did here, we have proved one result, that if lambda 1 less, if this lambda 1 less than lambda 1 C, where this is the critical value of lambda, then this parabola will intersects the Batchel and Gill semicircle. Okay, let me show you with the graph with the valid example, and we have compared this our result with the existing result which is done